followed something we'd done about 10 years ago with the more of a California focus. And I went and I talked to Andy and Neil and Mike, and they all said yes. Then I realized I had other things to do. So I said, well, let's put it off into the future. And I want to first thank Mike for saying, no, we don't put this off into the future, let's just get it done. But then the problem is who gets it done. And so I really just want to point to Hannah. Hannah's the person that's actually made this happen. She's also the person that's brought most of you here. This is not something I like to dump on the lap of a first-year assistant professor, but I just want to emphasize just how important that work really was. Today we have one last panel. It's our last set of presentation. I just want to frame it in a couple ways that follow from discussions that we had yesterday. So understanding water quality is a complex scientific and engineering problem. We saw this with discussions of PFAS. We saw this with discussion of understanding the ocean salinity. We know there are satellites out there that can tell us lots of things, but we're not quite sure what to do with all this data. And then the other part that we heard yesterday is some things have price tags in the millions. Some things have price tags in the billions. When you get down to 20 centimeters of sea level rise, the price tags are in the trillions. So getting policy right is important because, in fact, resources to address water quality are scarce. If you go to thinking about even Central Valley issues to mitigate certain sets of environmental impacts, they're complicated. So figuring out the practical, the urgent, and the feasible is where this conversation, I hope, will lead us. And what economists and social scientists need is this interaction with the science and the best science that we can do to really understand where we can actually have a big impact. So that's what this panel is hopefully going to deal with. It's also the largest panel, so we're going to run a relatively tight time shift. And our first speaker is Hannah Druckenmiller, Caltech Assistant Professor of Economics. Will be followed by David Keyser, University of Massachusetts Amherst, in Resource Economics. Megan Mullen from UCLA, who's the faculty director of the Luskin Center for Innovation. Laura Taylor, who's a postdoc at Caltech. And Hao Zhao, who's coming from Linde University in Beijing, and is a Caltech teacher. So, Hannah, without further ado.
Thank you, Jean-Laurent, and thank you everyone for being here again today. I'm really excited to continue the discussions. So one of the broad goals of this workshop is to find areas where water quality science can be more tightly linked with decision making. And what I want to do in my brief time today is talk about the challenges to doing so in the context of non-point source pollution. So we heard a lot about non-point source pollution yesterday. This is extremely damaging, but it's also hard to control because we often can't pinpoint the source. So for this reason, non-point source pollution is currently considered the leading remaining water quality challenge in the United States by most states in the US. And this is despite a very large scientific effort that tries to understand non-point source pollution from a variety of angles. There's lots of research, we saw some from Jenna yesterday, trying to understand the sources of non-point source pollution and where it ends up. There's lots of studies that look at the impact of non-point source pollution on human systems and on natural systems. And there's also a large literature that tries to understand what types of control measures are most effective at mitigating non-point source pollution. But despite this, policymakers actually don't have a very strong evidence base on which to base decisions about what works and what doesn't when they're controlling non-point source pollution. And the reason is that there's very mixed results as to what works and not. So Zach gave us a great example yesterday when he was talking about the CAS model and the Chesapeake Bay, and we saw that oftentimes what scientists will do to try and measure the impact of best management practices is they model the impact of best management practices on water quality, they measure how many people take up that intervention, and then they model the water quality benefits. And if you do that, it looks like our best management practices are working. They result in water quality improvements. But this study of over 100 best management practice interventions echoes exactly the story Zach told us yesterday, where when you look at actually the empirical data, we see a different story. So now we actually see when we look at empirical measures of water quality, there's not a clear link between the adoption of best management practices and water quality improvements across a broad range of contexts. So I want to get at why. Why are we not seeing improvements in water quality when we look at empirical data, and how can we reconcile that with models that tell us that we should be seeing? one reason, which is that models are trained on data. So they're not made up, they're calibrated to real world data. But the type of data that they're calibrated to is very different than when we implement these interventions at scale. So usually these control measures are originally investigated on small plots at maybe the field level that are relatively homogeneous and over a relatively short time scale. And so this, here we get some evidence that these best management practices do in fact reduce nutrient loads. But then we try and scale up these interventions to the watershed level and evaluate them using observational data, and we find much more mixed results. And so for this reason, more data has not always led to more effective decision making. So I want to just highlight one project that I'm working on in this area that I think provides a framework through which we can see some kind of broader challenges in the study of management practices. So one program that I'm really interested in is the Conservation Reserve Program. This is the largest private land conservation program in the United States. It enrolls about 25 million acres of land. For those of you that aren't familiar with the CRP, essentially what it does is it pays farmers to take land out of agricultural production, and most often to also restore some of the ecological function of that land by, for example, planting native grasses. This program targets water quality improvements in a number of ways. First, by reducing the amount of land that's under production, we see lower fertilizer use, and so we should expect lower nutrient loads. Additionally, riparian land is highly prioritized for enrollment into the program, so we should expect reduced nutrients as those buffers are intercepted in pollutants before they enter our streams and rivers. And lastly, wetland restoration is prioritized again with this program, which can act as kind of a natural filter. So what my research team and I are trying to do is understand at scale, using real world data, what is the impact of the CRP on water quality? So instead of just looking at an individual plot, can we look at those 25 million acres and understand what their impact at the watershed level is? So to do this, we're partnering with the USDA, and we have field level information on enrollment, so we can see every field that's enrolled in the program every year. And at first, we were like, oh, this is a kind of a really nice natural experiment. We could look at water quality readings directly above the enrolled fields, directly downstream of them. We can look at how that difference changes over time when a plot is enrolled, and then we can get the causal effect of the CRP on water quality. But when we try to implement this in practice, we run into a number of empirical challenges that I think are actually common across basically any study that tries to look at the influence of management interventions on non-point source pollution. So the first thing is that there's really long time lags between when these management practices are implemented and when we expect to see a change in stream water quality. And like we talked about yesterday, this is largely because there's a lot of these nutrients that are built up in the soil. So for example, if we stopped using phosphorus today, it's not like we turn off the phosphorus, the faucet, and we no longer see phosphorus in the stream. There's all that phosphorus built up in the soil that's going to continue to seep into the streams and rivers. So this makes it hard not only to statistically detect the effect of these interventions, but it also really makes it hard to get buy-in from farmers and policymakers who want to see kind of results from these interventions on shorter timescales than years or even decades. Okay, in addition, we have simultaneous drivers and multiple causes of non-point source pollution. So again, in Zach's talk, we saw there's a riparian buffer next to a stream. We think it should be improving water quality, but at the same time as that intervention is introduced, the farmer now has more cows on his land, and so we actually see deteriorating water quality. In addition to kind of changing agricultural practices, we have changes in weather that might change water quality. And teasing apart these multiple drivers becomes extra difficult when you have these unknown time lags in the effect of the intervention. We also lack consistent monitoring of water quality over space and time. So what we really want is we want a before and after, and we want this at fine enough spatial scale that we can look at the effect of these kind of really local interventions. But as I'll discuss in a few minutes, oftentimes that data simply doesn't exist. And then lastly, there's really rich heterogeneity in these watersheds, both in terms of natural characteristics and in terms of social systems. And so an intervention that works somewhere in a field study might not actually transfer that well to a new context. And in addition, when we look at these things at the small scale, we're missing kind of important interactions between watersheds or spillovers among them that could lead to different outcomes at the large scale than we see at the small scale on which most of these interventions are initially evaluated. And so I didn't come up with this phrase, but water quality has long been called kind of a data-rich but information-poor environment because we do have lots of measures, but it's actually kind of hard to learn from them of what we should be doing and what we population. So I said data rich, but maybe I'm just being greedy, but I'm going to argue that this environment isn't actually as data rich as you might think. And I'll use the water quality portal as an example. So the water quality portal has over 300 million records of water quality readings across the US dating back decades. It's an amazing resource that the EPA has made available. But it's not perfect. It really lacks data at refined spatial scales. So if you go down to the sub-watershed level, this study looked at HUC 12 level, only about 20% of sub-watersheds are actually monitored. And that number is even lower in agricultural areas where non-point source pollution is a bigger deal because monitoring closely tracks population levels. So the population is much better represented than land area, but that means that rural areas tend to be underrepresented. The second issue is that measures are infrequent. So the average monitor in this data set only has a reading once every 4 months. That becomes really challenging when we try to link the data with kind of high frequency events like rainfall, which we saw in Bryn's talk was really important for understanding non-point source pollution levels, if we can't actually link kind of high frequency events with high frequency water quality readings. Third, these data come from very fragmented sources. The majority of them come from state agencies, but each agency has its own different collection procedures. We also get some data from tribal authorities, municipalities, nonprofits. And what this means is that these data all need to be harmonized before you can actually use them together in a large-scale study. And most often, the metadata that you need to harmonize them is missing. So several studies have found that over 50% of these records lack basic metadata, like what chemical form of the pollutant was measured, so they're actually rendered unusable. And then finally, there's a couple of nice studies done in the US, but some in New Zealand and Canada, that even if we expect a certain level of treatment from a best management practice based on modeling, often water quality data is sparse enough that we could not detect that level of effect in a real world sample because we simply don't have the power to do so. So right now, we have all of this tremendous data, but again, it's not really leading to changes in decision making. And I'm representing the social sciences today. I want to bring up a table from actually Dave Kaiser's paper. So I checked your slides. This isn't in there. This is a really nice paper by Dave and Joe Shapiro that looks at kind of the difference in social science research and economics research in particular into air quality versus water quality issues. And they find that air quality is much better studied by social scientists than water quality. And this isn't because social scientists are inherently more interested in air quality. In my opinion, it's because we kind of lack the data we need to actually take these data off the shelf and input them into our common research designs. And so one kind of striking number from this table is that if you look at the top 5 economics journals, which kind of set the research agenda for the discipline, at the time of publication, there was 45 papers on the Clean Air Act in these journals, and there was only 1 on the Clean Water Act and the Safe Water Drinking Act, also Dave's paper. So if I could wave a magic wand and change something about the way that we monitor water quality to make it more compatible with social science research, here are 3 things that I would do that I don't think actually require new technology, just changes in the way that that technology is deployed. So first, we have this large network of water quality sensors, but they're giving very infrequent and irregular readings. If we could even focus on a smaller subset of sites, but get frequent and sustained readings over long time periods, I think that would really help in the social sciences domain. Additionally, it would be really nice to not only monitor water quality in places where we've introduced interventions, but try and strategically select kind of comparison watersheds to help with the inverse problem. So getting measures in good controlled areas. And then finally, this is a super low cost thing that I'm hoping a scientist in the room is willing to do, is all of those data records on the water quality portal, if we just harmonized them one time and made the harmonized data set publicly available, that would make an off-the-shelf data record that all of the social scientists like me who don't necessarily know how to do the harmonization ourselves could go to and use immediately. And so there's kind of a nice paper that came out of a lab at Berkeley that I used to be associated with that does this for nitrogen and phosphorus in the Mississippi River Basin, but we could do this at a much larger scale everywhere in the US and for much more pollutants. So that's just my 2 cents on kind of what types of measurements would make social science research more productive in this area.
Hannah, can I ask a question just while we transition?
Yeah.
How much time went into that